Go 7:30.
Time for it, na. Time for it, na.
Make time for it.
For eating. Peacefully, relaxedly.
Yeah, banana, na.
Okay. Coming back to our linear regression. So last class, so we have tried to model this linear regression to our dummy data set, right? So when you model means you are actually trying to obtain these values. Intercept meaning this is your C, this is your M, right? So for your data, whatever the data you have here, after model fit, you have obtained a certain line of best fit for which you have got some intercept value and some coefficient value returned by your algorithm. Now, after you obtain this line of best fit, you can always find out the corresponding value for Y for some unknown values of X, right? For those values of X for which you don't know what Y is, you can use this straight line to predict the same, right? So your linear regression, it is one of supervised machine learning algorithm. It is parametric in nature. Parametric in nature means it is defined by a set of coefficients, right? It is parametric. Yes. After. Yeah. Suppose you have obtained this. And your algorithm has returned you your line of best fit. That is what your algorithm claims, right? But you have to check how this line of best fit works for your data. How do you check them? You will try to find out the errors, right? How do you check the accuracy or the efficiency of your linear regression? Whatever the linear regression modeling you have done for your data set, how do you going to check for the accuracy or the efficiency of that model? For that, you will have a look at the error terms, right? Out of multiple error terms, last class we saw this one, right? I showed you one, this one, mean squared error. Your sklearn library provides you metrics, from which you can call mean squared error. You also have mean absolute error, okay? So a low value, a minimum value of this mean squared error. When a mean squared error almost near to 0 will indicate that whatever the line of best fit that you have obtained, it is almost passing through every points, right? It is almost near to every point in your data set. But the point is you cannot simply rely on these error terms, be it mean squared error, be it mean absolute error. You cannot simply rely on them. You have to look for other factors as well. You have something called coefficient of determination. Okay, why can't we rely on these MSE, MAE means? Right now, though, your data set is this one, right? Following this pattern. It may happen that you have a data set with values here also, some values. They cannot be called outliers, right? And even in that case also, there is a chance that you are getting MSE value almost near to 0. Okay. Now, so as to confirm that your regression model is working just fine for the data set, you have to have a look at R square as well. Okay. Now, what this R square tells you is, R square is actually, let me have this first. Let me show you this figure. Look at these terms. Suppose this is your line of best fit. These are your axes. Wait. Let me here itself. And this is some data point, right? Let us focus on this first. Somehow you have got this, not somehow, using your simple linear regression, you have obtained this line of best fit for this data set. Okay. If this is your line of best fit, then for this X, you have this predicted value for Y. Okay. Suppose the mean value for Y lies here. Fine, this Y bar. And this Y is the actual value corresponding to this X. Okay. So corresponding to this X, you have 3 different Y's here. One is the true value of Y. Another one is the predicted value of Y. And this is the average value of Y. Okay. In linear regression analysis, you have actually 3 error terms, which this one is this one. This is called total error term. Also called the total variance. Okay, total variance observed. Next, from here to here is the error that could not be explained. These are also called variance, okay? Remember this term. Why variance? We have already seen, right? One error term I have defined earlier, right? What was it? All y's minus the predicted y. Suppose this is the predicted y minus the actual value of y whole square. Looking at this expression, do you remind any statistical measure? Does this expression reminds you of some statistical measure?
Squared residuals.
Residual too. These are residuals. These error terms are residuals.
So, ma'am, here actual you are subtracting actual minus predicted.
No, I'm just asking about this expression. Does this expression reminds you of something that you have seen earlier?
Like
Residuals, yeah, looking at it now, no?
ordinary least square.
Does it not resemble the variance formula? How do you find the variance for a data set?
Y minus x minus mean of x. Sorry, yeah, sum of a square of x minus mean of x divided by n.
Yeah. Suppose we leave out n for the time being. Does not it resemble the expression for variance? That divided by n is so almost like the scaling factor, right? It scales the value. If you just forget this n, this expression resembles the formula for the variance, okay? That is why in many of the books or many of the articles, you will see people referring to these as variances, okay? So this is the total variance observed in your data set. This is called the unexplained error or the unexplained variance in your data. This one is your explained variance. Your R square is actually the ratio of explained variance over the total variance. Okay. Now, these terms might confuse you, but you can observe it. Okay, before reaching here, can you tell me what?
From my point of view, total error has to be y minus y bar.
No. Total error is not. No, there is nothing, there is no issue with this. I'm just trying to make it little simpler for you. This is total error, okay? Total error in the sense, this is the actual and this is the predicted one, right? Hence the total, hence it is called the total, okay? I'm just trying to make it little simpler. Okay, can you tell me without involving any mathematics, what this y bar represents?
That is mean of the.
What is mean? What does mean represents? Mean to tick, but what does mean represents? Why do we need mean first of all? Why do we need mean?
Because
get the
mean
average.
gives
An
the
average.
mean gives the
Why do we
central
need
tendency of
average?
mean gives the central tendency of the data, and here we are comparing, so that is the reason we are taking mean. So we should take some measurement who gives the central tendency of the data. We should have some
Why do you
scale.
need central tendency?
See that in which value or most of the data lies.
Meaning mean actually is a representative of all the data you have, right? Mean actually represents all the data in your set. Like, can we say this way?
Yes.
Mean is
Yes.
actually a single number. Mean is actually a single number represents the data in your set, in your data set, right? So, and what about variance? In the same way, what about variance without involving mathematics? What is variance?
Variance is the distribution from the mean.
And what does that distribution indicates?
How far the data points is from the mean.
Okay, if you know how far the data points are from the mean, then what do you get? What does that indicate? How does it help? How does the variance value help?
Like if we go if I talk about the standard deviation, if I go one standard deviation, both of the sides left and right, will get the 65%
You are
of
going
the
too
data.
far. You are going too far away. Okay, I want to avoid those mathematical details. In the simplest layman term, if I need to explain. Yes, this is correct that variance represents how scattered are the data from the mean, right? How scattered are the data from the mean means it in a way shows how faithful is the mean for your data set. Can I say? If the variance value is much high, is on the higher side, can I say that in that case, mean is not a good representative for your data set? Agree?
Yeah.
Yes. Like if suppose you imagine a situation, huh? Suppose Praveen sir has a number of students, right? Like you all. He has team of many students, huh? Suppose 100, 200 students. And suppose he wants to gift all of you a t-shirt with Yoshops logo on it. Huh? What will he do? He will try to order for the t-shirts, right? Now, if he orders for the t-shirt, will he give the measurement of each one of you specifically to that person? No, right? What he can intelligently do is he can find out the average size of the t-shirt for the team, isn't it?
Yes.
And he can just tell the particular person that he needs the t-shirt of this size, right?
Yes.
Suppose if the situation is ideal, this idea works, isn't it? If the situation is ideal meaning if the variance value is low, then that average sized t-shirt will fit almost all. Suppose the variance value in this case, in this particular t-shirt case is high, meaning what? The size of the t-shirts varies, right? It varies significantly from one student to the other. In that case, the mean makes no sense, isn't it? That means the variance in a way gives an indication as to how faithful is the mean for your data, right?
Right.
So that is why when you go for error calculations and all, you almost always look for expressions that resembles the variance thing. And mean always comes into the picture, right? Mean being a singular representative of your whole data set, and variance being a measure of faithfulness of the mean for that data set. Okay. So that is why in this particular picture, you will observe this variance and the mean terms. Now, these are the nomenclatures, okay? Now, regarding these nomenclatures also, this is your y, the true value. This is the predicted value for this y, predicted value. This is what you have been targeting for throughout, right? So this difference has been named the total variance term, total error, okay? And with respect to this mean, how far is your true value? How far is your predicted value? Tells you about the unexplained and the explained variance. Okay? Fine up to this? Now, if you have a line of best fit, the thing is, this unexplained variance should be minimum, isn't it? Minimum means what? Your line of regression should always go past near this point, right? If it is far away from this means what? The unexplained variance increases. Now, the thing, there is another thing, why this is unexplained and why this is explained variance. Why not this unexplained and this explained? That can be another question, right? Now, this is explained variance. Why? Because you know how this difference has arisen, right? Why is this difference? This means you know it represents your data set, right? And this is the line of best fit that you have obtained using your algorithm. So somehow you understand why this error appears here, because it is approximating the data set, isn't it? So whatever the portion remains, we actually don't have any solid reasoning for that. So there might be many issues that might be there in the data set, which we don't wish to define at this moment. We just wish to minimize it. Hence, we are calling it unexplained variance. Okay. This thing though we cannot move, na? We can simply move this one. That too depends upon our criterion, right? What we have decided, how to find the line of best fit. Fine up to this? Can I get a quick okay or no, whatever?
Yes,
So
ma'am.
there are two things, yes. So there are two things that are important when you study linear regression analysis, okay? One is though how your algorithm is obtaining that linear regression model, meaning those parameters, MC or M1, M2, Mn up to C, okay? And another thing, I'm telling you this from preparation, interview preparation point of view, okay? So these usually comes if the research or the survey has to be believed. So these are some popular questions. Just keep this figure in mind so you won't confuse. So instead of delving deep into the mathematical details, I tried to go little conceptually. I hope it helps. So these 2-3 lines of codes, behind these 2-3 lines of codes are actually all these things running. So next time what we will do is, we will take one real data set. Okay. I will find out one proper data set having certain issues, and we will try to model, okay, using LR, linear regression. More once though for that data. Am I think covered? Yes. There is one more thing. Actually, this regression analysis is such huge that you can spend your entire lifespan studying it by its breadth, by its depth. But for the time being, you can focus simply on linear regression. Even linear regression, if you wish to go in depth, it will sticks behind it. I have tried to touch upon the things briefly. Even after this, one thing remains. Okay, those are also important. Assumptions. Before even thinking of using linear regression for your data set, you have to understand what are the assumptions that has to so your linear regression model works faithfully for your data set. Okay, that is another significant thing that you have to understand. Assumptions. So assumptions we will again cover next time when we deal with that data set. Okay, along with the data set, we will try to understand the assumption. Obviously, the assumption is that
Yes, okay. I'm going to
independent variable and the variable. What happened? They have to follow a linear relationship, right? That is one obvious assumption. But apart from that one, there are 3 to 4 or 4 to 5 more assumptions. So next time we will try to understand that in detail, along with the data set, along with code. So maybe that will interest you. So that's it for today. Any question?
thank you, madam, for valuable training session given. Anyone have any question? Ask now. Either I am going to close this meetings. No question. Now I am going to close this meeting right now. Thank you, everyone. Have a good day. Bye. Thank you, madam, for the training session. Thank you.
Thank you, sir.
Bye.
Thank you, sir.
Thank you. Thank you, madam. Bye.